All right, let's talk about sigma notation. We've all seen it, but its real power is so much more than just a neat way to avoid writing a bunch of plus signs. Today, we're going to see how this one symbol is basically the engine behind huge ideas in calculus, computer science, and even how we analyze data today. I mean, just look at this. Imagine you had to add up every number from 1 to 100. Writing it out like this is, well, it's a nightmare, right? It's slow, it's clumsy, and you're almost guaranteed to make a mistake somewhere. This is exactly the kind of problem that gets mathematicians thinking.
And you'd be right. There has to be a better way. You see, math is all about finding elegant and efficient solutions. And whenever you see a tedious, repetitive pattern like this, it's a huge clue that there is a more powerful tool just waiting to be used.
And that brings us to the hero of our story today, Sigma. So let's do a quick refresher on how this thing is built before we get into all the cool ways we can actually use it. And here it is, the Greek capital letter sigma. At its heart, its job is super simple. Add everything up. But just calling it a symbol for addition is like saying a supercar is just a way to get groceries. The real magic is in what it lets you do. So let's get the official definition out of the way. It's a way to write a long sum concisely. And yeah, the fact that sigma is the Greek S for sum is a nice little memory trick, but we're here to go way beyond that. We're here to unlock its potential. Okay, so every summation has these 4 key parts. Think of it like a little piece of code. The lower limit on the bottom tells you where to start counting. The upper limit on top tells you where to stop. The index, that little I, is your counter. It's going to tick up one by one. And then the expression right next to it, that's the recipe. That's what you do at every single step of the count. So actually reading 1 is like following a simple recipe. You start with the bottom number, plug it into the expression, and add that to your total. Then you go to the next whole number and you do it all over again. You just keep repeating that loop until you finally hit the number at the top. It's a step-by-step process that makes it so perfect for computers and so fundamental to things like calculus. And here's a little bit of trivia for you. We have the legendary mathematician Leonhard Euler to thank for this. Back in 1755, he needed a better way to write down all the crazy infinite series you find in calculus, and this was his genius solution. Okay, so we know what it is and how to read it, but the real fun, the real power, comes from knowing the rules of the game, the properties that let us simplify and solve things in ways that feel like a superpower. First up, rule number 1, and this one is a game changer. If every single term in your sum is being multiplied by the same constant, you don't have to do that multiplication over and over again. You can just pull that constant out to the front and multiply just one time at the very end. It's a huge time saver. And rule number 2 is just as powerful. If the expression inside your sigma is 2 things being added or subtracted, you can actually split that one big, complicated sum into 2 smaller, simpler ones. This lets us break down a tough problem into pieces we can actually manage. Now, a super important warning here. This is the number 1 mistake people make. You can totally break up sums and differences, but you absolutely cannot do the same thing for multiplication or division. The sum of a product is not the product of the sums. Please, please burn this into your brain. All right, now for the best part. We've got the notation, we've got the rules. Now let's get to the shortcuts, the formulas that let us solve these massive sums in literally a single step. This is where we get our superpowers. Think of these as the ultimate cheat codes for these really common patterns like summing up a constant, or all the integers squared. Mathematicians have already done the hard work and given us these beautiful formulas. And that's sum of I squared. That's not just some random textbook problem. It's essential for calculating things like standard deviation and statistics. These are some seriously powerful tools. So, let's put it all together. We're going to take our rules, we're going to take our formulas, and we're going to solve a problem that would be an absolute beast to do by hand, just to show you how slick this whole system is. Here's our challenge problem, courtesy of Paul's online math notes. We need to find the sum of 3 minus 2i squared for every integer I from 1 all the way to 100. Let's walk through it step by step. Okay, first things first. That squared expression inside is kind of awkward to work with. So our first move is just to do some basic algebra and expand it out. 3 minus 2i squared becomes 9 minus 12i plus 4i squared. We haven't changed the value, we've just made it easier to work with. Now remember rule number 2, the one that lets us break things apart? We're going to use it right now. We take that one summation and split it into 3 separate, much friendlier summations. One for the 9s, one for the negative 12i's, and one for the 4i squareds. Next up, rule number 1. We've got these constants hanging around, the negative 12 and the 4. Let's just pull them right out in front of their respective sigmas. See how clean that looks now. Each sigma is just one of those basic forms we saw in our cheat sheet table. And here, this is the magic moment. We're going to go through and replace every single one of those sigma expressions with its formula. We just plug in 100 for n, and suddenly, this isn't a summation problem anymore. It's just arithmetic. You crunch all those numbers, and what do you get? 1,293,700. We just calculated the sum of 100 different terms without doing a single bit of repetitive addition. That is what I'm talking about. That is power. This quote from Varsity Tutors really just nails it, doesn't it? It's not just about making things look shorter. It's about creating a clear structure that we can actually work with, manipulate, and solve. So remember that first problem? Adding every number from 1 to 100? With our formula, it's just 100 times 101 divided by 2, which is 50-50. Easy. The secret is that this isn't just a math trick. It's a fundamental tool. It's the engine running under the hood of so many things. So now that you know how it works, what are you going to build with it?